Robert is a senior transportation engineer who has been with Caltrans since graduating from the University of California at Davis in 1998. He spent 5 years working in roadway design and construction on the I-80 corridor before moving on to pavement engineering, where he has developed policy, guidance, plans, specifications, and recommendations for asphalt, concrete rehabilitation, in-place recycling, reclamation, foundations, life cycle cost analysis, and pavement evaluations and management. Most recently, Robert spent 5 years developing improvements to Caltrans concrete pavement repairs and preservation practices. Help me enjoy. Welcome, Robert Hogan. Robert.
Thanks. It's nice to be here. Just going to start with some quick background on our network. Caltrans has about 50,000 lane miles that we're responsible for. It's about 14% of the network, and of that 50,000 lane miles, about 15,000 lane miles or 30% are concrete. And our highways carry about 55% of the vehicle miles traveled, even though it's only 14% of the network. Quick financial breakdown. Over the last 4 years, we've done about $4 billion worth of work, and that's covered 16,500 lane miles. Our average cost for preventive maintenance projects is about $100,000 a lane mile. And for major rehab, we're at about $1 million per lane mile. And our 10-year needs are estimated to be about $2 billion a year. A little bit about our traffic and climate. The number of trucks on our roads is going to more than double in the next 20 years. We carry a lot of freight from Asia. About 60% of all goods from Asia come on truck or rail through California. And as far as climate is concerned, we break the state into 9 different climate regions. That's based on precipitation, temperature, and temperature swings. For us, cracking is our predominant distress for both AC and concrete, and so that's how we've set up our pavement management system. For concrete, we basically look at first stage and third stage cracking. First stage cracking is just a single longitudinal or transverse crack, and what we call third stage cracking is intersecting cracks that create 3 or more pieces in the slab. And so for our strategies, we correlate preventive, corrective, and rehab based on distress over a lane segment. For third stage cracking, we're also looking at additional criteria such as crack width greater than 3/4 of an inch or settlement greater than 1/4 inch before we go to slab replacement. Today, I'm mostly going to focus on spall repair, Dabar Retrofit, and slab replacement. But as far as rehabilitation goes, we consider rehabilitation when we've got third stage cracking over 10% of a segment, and we do a life cycle cost analysis between 10 and 20%, and if we're over 20% third stage cracking, we generally favor rehab. So about 5 years ago, I was tasked with improving our spall repair practices. Got a lot of reports from the district that basically spall repairs weren't working, but management wasn't really interested in putting a lot of money or research into the issue. So it wasn't possible to decide whether it was design or materials or construction issues that were the problem. So I did some background, and luckily, like when I was in the middle of the process, the CP Tech Center came out with this guidance. And so essentially I just borrowed that and considered it to be the most up-to-date guidance I could find. And that's a look at the standard plan that we developed based on the CP Tech Center guidance. It's just a typical spall repair, and it's pretty, the only unique thing about it is this sloped surface. Typically our practice was to saw cut a vertical boundary, and now we're calling for a saw cut, but we're also calling for a 2-inch chip out between 30 and 60 degrees to create a rough slope surface for improved bonding. The only other difference would be, we've got a minimum size on the repair now. Before, you'd see a lot of small spall repairs. inspectors weren't really actually determining the soundness. They were just chipping out the damaged area. And so those are the two kind of main features. And previously we didn't have any detail at all for design. So it was important for us to at least show something in the plans, try to rein in the practice. Here you can see the blue arrows are kind of pointing to the area that's going to be chipped out beyond the saw cut. Accomplishes a couple things. It provides that rough sloped surface for bonding, and it also gets rid of all this run out from the saw cut. It's still something we're working on communicating to the districts. I've traveled to some projects and find that, you know, it's kind of business as usual. They're not even really looking at the detail or the specification. So the other thing that's somewhat unique is right now we're using only polyester concrete for our material. Historically, we'd allowed cementitious material and polyester, but because of some of the issues we had, we just decided to go ahead and go with polyester, even though it's more expensive. Since it's such a labor-intensive practice, we want to make sure that we're using the best material we can. Polyester concrete, if you're not familiar with it, it's just a mixture of aggregate and polyester resin. And the resin acts as a cementing agent, but there's no Portland cement. It creates a durable patch. It's got a lower modulus of elasticity than concrete, and it has a higher tensile strength, so it's tough, and it bonds well. But you do have to reform the joints or cracks that go through the area. So here's a look at a non-polyester spall repair, and hopefully if we're using polyester, it's never going to end up looking like that. We have had some issues. Polyester was used on our bridge decks, and so to us it was a common material, but we found that, you know, some of the repair crews weren't so familiar with it, so there's been some issues with batching it in smaller quantities and applying it out in the field. For future innovation, we're looking at expanding the materials that we use. We're going to go to hopefully to an authorized materials list setup. That way we won't have to do as much project-specific verification testing. And those are the categories we're looking at going to: polymeric, cementitious, and then hot applied, similar to what was demoed yesterday. And some of these materials too, we're looking at using for widened longitudinal joints, which is an issue in some of our southern districts. It's been a challenge to get this done. We have a lot of resource issues when it comes to developing new materials requirements. And so we're looking to actually complete that through consultant task order at this time. So for our corrective strategies, we did a lot of Dabar Retrofit starting about 15 years ago, but we had some issues with it. And given the age of our network, we're not looking at it as a strategy that we're really going to use a whole lot. Our workhorse strategy is pretty much individual slab replacement. We do also do a lot of grinding. I'm not really going to talk about it today, but we did do a survivability study about 12 years ago, and it showed that we can get about 17 years of service life out of our projects. And that's based on a threshold of IRI increasing about 78% over that time. And the study also showed that most pavements can structurally handle about 3 grinds throughout their pavement life. And here's a look at a Dabar Retrofit job. The arrows are pointing to some hairline cracks. It's probably hard to see. We had some issues with workmanship in the beginning, getting the slots clean, using spacers. All that was a problem. And this is the same set of cracks 9 years later. And then this is a different slot, same job. One conclusion was that maybe we were opening to traffic too soon. So the requirement was changed from a couple hours to 24 hours, but given our high traffic routes, basically it rolled out Dabar Retrofit as a strategy. So similar to what we did for spall repair, we decided to go to polyester concrete backfill. We've only done a few jobs, but after a few years, we haven't had any problems yet. So slab replacement's basically our primary strategy. Most often we use cast in place concrete with what we call rapid strength concrete. It can be type 3 cement or it can be calcium sulfoaluminate cement. This is a picture of a slab replacement. Basically, the hole is about a third filled right here. They got a roller screed, and as they fill the hole, they finish it with the roller screed. So we've had some issues with performance on slab replacement, at least according to our districts. We've looked at it a couple different times. So we went ahead and did a survivability study. The original intent was to try to see if there was a performance difference between the two different types of cement, and we weren't really able to capture any difference. But some of the variables that we looked at were between doweled and undoweled replacements. So typically our standard design is an undoweled replacement, just replacing the existing thickness and kind. But we saw that for the slabs that were doweled, we were potentially doubling the performance life in terms of failure threshold of 10% third stage cracking. So you can see here that if you extrapolate in red, we've got the undoweled, blue, we've got doweled, and you can get twice as much service life on average. The data is a little scattered, and obviously there's some issues when you're using real project performance data to make these kinds of conclusions. One issue we had was, premature failures weren't captured, and also because we do a lot of, random slab replacement over the same locations, it was difficult to ID these slabs by their age. But one thing we are thinking about doing is go ahead and requiring dowels at all transverse joints. There's been some interest. We've got non-standard specs and plans developed, but we haven't done any projects to date. Another thing that we're considering is doing a thicker monolithic pour where we pull out the base. Most of our pavement has CTB under it, 4 inches of CTB, and it's variable quality. But typically on the job, a lot of times the base is left in regardless of whether it's in good condition or not. Something else we're looking at doing is reinforcement. We'd like to try macro or microfibers, but it's challenging for RSC because you have to modify the volumetric mixing trucks to accommodate the fibers. We have done some jointed reinforced jobs with using number 5-inch bar, 12-inch on center spacing. Something we were contemplating at the headquarters level, and then we found out that some district maintenance engineers were taking upon themselves to do this. So we're trying to get an evaluation together so we can track the progress. We also do a lot of precast work. It's still a non-standard strategy for us, but we have one district that really favors it. It is very expensive. So it's something we're still working through. There's intellectual property issues. We choose to specify generic elements of a system and then allow the contractor to propose alternatives. But there's been some construction quality issues from the general contractors. It's evolving. We're still doing it, but I think there's probably some issues that need to work out before it gets standardized. One issue that we deal with, a lot of other Western states like Alaska, Oregon, Washington have this problem too, is chain wear. Essentially, we get a lot of truck traffic on Interstate 80 over Donner Summit, and there's a lot of pressure to keep the route open, so there's a lot of plowing and a lot of chains are riding on bare pavement. we've basically overlaid this entire corridor using an unbonded concrete overlay within the last 15 years. And we've already had some locations that have already had to been ground twice due to rutting. So our goal here is to avoid doing that grinding. And we looked at a couple different things. We tried HMA Overlay, that didn't work. We tried bond and wearing course, that really didn't work. Grinding and grooving works for a time, but it actually wears faster. So we've looked into Lithiumsilicate surface hardeners, and recently also tried Polyester Concrete Inlay. Some background on the surface hardeners. Just the lithium penetrates the voids in the concrete surface. The silicate reacts with whatever free lime's in the paste, and it forms additional calcium silica hydrate. It is a proprietary product, so there's some issues there in terms of potential standardization. But we've done some lab studies, and it showed that there is some hardening benefit, and it does create some increased abrasion resistance. But we've had difficulty correlating it to actual field performance. So in terms of cost effectiveness, we're looking to try to figure if we can just determine what a good reapplication frequency is. We've done about 3 contracts so far. One of them was done with shot blasting. One of them was done with grinding. And one was an evaluation of 3 different types of materials. But in general, if you include the shot blasting costs, the hardeners are able to reduce the wear by about half, then we can show them to be cost effective. The problem is, with the time it takes to get a contract out, it's probably not cost effective to do it on a contract basis. So we're looking at potentially having our maintenance forces reapply it on an annual or perhaps even more frequent basis, just in the wheel pass in the outside lane. Some of the limitations, there's not much penetration depth. You're looking at about 5 millimeters or less. Once that wears off, you're essentially back to an untreated condition. And if you combine it with grinding, it can get very expensive. But if you've got existing rutting, you don't really have another choice. So we're looking at doing abrasive blasting, potentially just by sandblasting. But even with shot blasting, it can still be cost effective. Also, we're looking at different options, like maybe just sweeping or flushing it with water, blowing it with air, or maybe even doing no prep at all. In a couple of weeks, we're gonna do a short section with no prep at all and see how it actually performs. So some background on the Inlay Concepts. Back in the 80s, Caltrans did some full lane width overlays with different polymer modified materials, and one of them was polyester concrete. But the actual specification for the type of polyester that was used and the performance results weren't documented very well. And it is, like I mentioned earlier, a typical material that we use on bridge decks. And our bridge decks get a little bit better wear life than our surrounding concrete. But we're also working with the material supplier to come up with a special formulation for the resin. Hopefully we'll get a little bit more of a tricked out mix and get even better performance. That's a look at the inlay section we did about a year ago, last October. We looked at 2 different concepts. One was just kind of filling in the existing ruts with polyester, and the other was to actually grind each wheel path. The procedure we used, we diamond ground about 3/4 inch deep, 3 feet wide. But it can be a challenge to capture the wheel path, especially around curves, because the actual wear in the rutted out sections varies in offset. And then second thing we did was we abrasive blasted. For the non-ground section, that was to remove carbonation, and for the ground section, it was to remove the fins and the dust. And then the third step is to apply high molecular weight methacrylate, which acts as a bonding agent for the polyester concrete. then finally, we just placed the polyester concrete by spreading and finishing it. On the left, you can see a picture of a vibrating screed, but it was pretty slow, so the contractor ended up changing to a roller screed similar to what we'd use for an individual slab replacement. This was just kind of like a proof of concept project, and we were hoping to do it on a contract job next season. And finally, the last step is feather grinding for smoothness and then opening to traffic. And the polyester sets in about 2 hours. Quick summary on what we've covered so far. For spall repair durability, we looked at adopting the CP Tech Center guidance. We changed our material to polyester concrete, and in the future, we're hoping to develop an authorized materials list for polymeric, cementitious, and hot applied materials. For slab replacement, we use rapid strength concrete. It sets in about 2 to 4 hours. We do mostly night work in our urban areas, and they can get quite a few slabs a night if it's a good contractor. And then we also look at doing precast panels. Production rate's a little slower on precast, but we have some districts that really favor it. They think, they're convinced that it's going to perform better, but we do need to do some more work in terms of quantifying exactly what kind of life we're getting out of the precast jobs. And for our abrasive wear issue, we're looking at surface hardener and polyester concrete inlays, but we haven't really solved the problem yet. There's a quick plug for our concrete pavement guide. It talks about all our standard concrete pavement practices, discusses limitations, effectiveness, strategy, material selection, and design issues. It's set up to be like a desktop reference for our engineers, but if you're interested in what we do or how we do it, you could use it as a reference. It's still a work in progress. There's chapters that need to be written, and it also needs to be updated, but you can see it at the link there if you want. And then for the areas that we haven't addressed in our guide, we like to use the CP Tech Center guide. I was able to work on the development of this, the update of this guide, and I think it's a good source, good reference. Any questions? The question is, are we setting ourselves up for failure by not adequately addressing failed base? And I think the answer is yes. One of the issues is characterizing whether you have a base problem or not when you're actually scoping the job. And then the other issue is just costs. And basically districts are trying to spread that money as far as they can. And getting into the base takes more time, slows down the op, and then they're not able to get as many slabs taken care of. But it is definitely an issue we've addressed we're discussing with industry on how to better capture when and how to pay for base replacement. Right now, I think our focus right now is probably like looking at some other alternatives like reinforcement to try to bridge the gap a little bit. Yeah.